Hi, everybody. My name is Nikolas Stathonikos, and I'm responsible for the implementation and development of AI at our department of pathology at the University Medical Center in Utrecht, the Netherlands. And I will be talking about the implementation so far in clinical practice in our department and some of the challenges that we faced, some of the hidden technical issues that we came across. Now, when talking about AI and the application of it, there are some reasons on why people choose to do this, or why departments choose to go this way. And there are two types of motivation. One is extrinsic and one is intrinsic. So the extrinsic usually comes from the facts, so where what we face as a department from the outer world. And that has to do with the increasing volume of examinations that we receive every year, and the fact that we have to do those examinations with the same staff, basically, so the same amount of pathologists. So at the one end, we have an increasing amount of examination and a decreasing budget or other cost cutting measures. And of course, we want to do that while maintaining quality and improving patient outcomes. So it's a significant challenge for pathology. And I think these are challenges which are being faced all over Europe and all over and also by other countries. On the other hand, you have a internal motivation, and that stems from wanting to improve your own diagnostic workflow. And most of the time, these are things that our pathologists themselves would request. For example, I don't want to be doing this task, or this task takes a lot of time, or there's too many things going on, and I want to be able to, to focus on a specific case, or it would be nice to have some way of be able to triage cases that come in this way. The workflow or the load is dealt more equally among all specialists. And of course, it will be great to have extra readings per case. Make sure that every case is read more than 2 times. So when considering that, you have to look, okay, what can be achieved and what is not possible at the moment. And there's a lot of work being done from a lot of research groups which come up with very interesting applications with a high degree of confidence and great results overall. But for clinical practice, you have to think a little more practically and see what's actually attainable at the moment. So applications like that have to do with counting specific features or structures, or trying to detect specific features, or measuring, so getting the tumor stroma ratio. That requires to first know where tumor is, where stroma is, and then try to calculate the ratio between them, or detect glomeruli and try to figure out how big they are, or even do some whole site classification in more broad terms, as in like, oh, this is malignant, or this is benign, or there's a high degree of confidence that there's tumor in this slide. And a combination of all these applications can provide a sort of like toolbox to use for automating procedures or diagnostic tasks. But there are also other types of applications which are more a little bit more far-fetched for a clinical application, which have to do with biomarker discovery, or having extended microscopic observation. Having a model look at a slide and be able to produce an exact microscopic transcript. And there are some interesting applications out there, but they're not so far there that they can be considered for clinical application. So when beginning this process, you're first confronted with the fact of, okay, how will you implement an AI model? Will the user or the pathologist have to do an action, or will this run in the background? And of course, both are viable options, and they have to do with what sort of type of task you want to automate, and how do you want to support specialists. So for example, tools that are user initiated, these will usually run in the viewer. So then the user will select an area, and then that's this area, the application, the viewer will then send that area, those pixels to be analyzed by the model. You will then get the results back, and then you will show them on the screen. And then either the user will have to correct the results or just show what the algorithm found. And this is one of the applications which I will get into further on. There's a presentation of how we implemented this in a department where a user selects a specific area, and then that area gets analyzed, and then it detects all the mitotic cells, and then the user can then correct that detection by classification or not. So there are several ways to implement these types of AI, and one other type is to implement a background a job scheduling system. So for example, a model that runs in the background, and then when the user opens the slide, it then already presents the results, or based on the model analysis, the case gets then prioritized in a sort of severity, and that's and there are several projects that have developed, but also commercial applications that do that. This is a research project out of our radiology department here in the University Utrecht, where they developed a system which combines which is workflow driven, and also does this job scheduling, and also syncs the results to the fax. So then the system knows which type of examinations are done, and then accordingly finds jobs to run on, or AI models to run on those examinations, saves the results, and then when the radiologist opens the case, they have an extra stream next to them, the results from the AI model. So this is great when you want to, when you want things to happen outside of user time, right? So one of the issues, let's say, or one of the we face is that there are a lot of research groups working on these AI models, but in order for them to come into production, we have to go through a whole process. And of course, you have the research phase of it, which is, you have to develop a model, you have to collect the data, somebody has to add the data to train a model, and then based on that, you can then validate your model on a separate data set, optimize, and then go through that process the whole time. And that's the research part of it. But that's only a small part of the whole process, because once you have a model which runs on your research data and on your validation data, then comes the actual work to implement a production, and then there's a lot of questions that come on it. First of all, you have to select a certain architecture, and then once you have it in production, you have to do some sort of pilot study. You might also do a shadow development, or deployment, where the algorithm runs, but it doesn't show the results to the specialist. You only review them afterwards and see if your algorithm agrees with what the specialist has already indicated. And once you've been through that phase, and now the model is ready, then you actually can bring in production. And then once it's in production, you still have to go you still have to have a lot of processes in place to do that. For example, you have to have some sort of monitoring. You might want to have some sort of active learning, where you keep all the answers that the specialist gives. If they agree or not agree with the algorithm, then you use that back in order to retrain your model. And then you might have to update your model, which then means that you have to go back and then do again all those steps that you did in the first place. So that requires to have a lot of things in place in order to do that. This is a slide from a paper from researchers from Google. They discuss about the technical debt that a model incurs. That has to do that the reality is that the machine learning code from model is actually a very small part of the whole picture, right? Because you have also the data and all the other systems that you have in place in order to be able to run that code. And in this slide, it shows from that perspective, from Google's perspective, what else has to be in place in order to be able to run that code. So when we bring that into a more medical application, and again, this is another slide, which shows that the machine learning code in the middle is a small block, and then you have all the other blocks around it, which have to do with data analytics, model version control. You have to have some data verification, the labeling. You have to be able to keep track of your model, and then detect if there's any degradation. So maybe your model goes back over time. So this is the complete picture of what has to be in place, or might need have to be developed in order to be able to do this in practice. So yeah, and looking into in our department, for example, what are we faced with? Of course, you also have the technical part of it, which is okay. Where are we going to host actually these models? How are we going to run them? What kind of system is it going to be? Some sort of a cloud environment? Are we going to use a high-performance computer, which might be co-located in our university, or maybe some local cluster? And of course, that's only the hardware part of it. And going into the software part of it, you have to keep your code in a repository, being able to have some sort of versioning, and being able to track changes. And the same thing also is applied for models. As soon as you make a new model, you have to be able to keep track of which version it is, and of course link that to the actual experiments that you did, or the training parameters that you used in order to bring it into that state. In order to do that, you have to also to keep your training data. So for every model that you train, you also have to have the original training data that you had in order to be able to recreate the model. And once you have all of that in place and you are able to run models, you of course have to do integrations, either with your PACS, with your LIMS systems. You might also want to be able to apply some structural reporting. So you want to be able, your model, to output some text in a structured way, which will go then to the report. So all of these things, they have to be in place, or they have to come into fruition. And it kind of looks a little bit like an iceberg, right? Whereas in the top is what we see, what we need. Yeah? So for example, we want to have AI in pathology. We want to be able to do more quantitative diagnosis. We want to be able to improve the reproducibility of what our specialists are doing. And then, what comes on our screen, what do we see? Do we see heat maps, coordinates? Do we see annotations? Do we get a structural reporting? Do we get some sort of prioritization, some sort of severity indication? And that's only just a tip, right? Because below that, you have all the processes that you have to have in place. How do you retrain models if need to be? How do you keep that a registry? How do you know what kind of experiments that you run? And then, of course, is it a background AI? And how is that triggered? How is that connected to workflow? And how do you keep in track which jobs are running and which are not? And then you also have the hardware. Do you use CPUs? Do you use GPUs? What kind of databases do you keep all your results? Do you use general hardware, or do you use very specific hardware? So like the Google TPUs. So these are all choices that you have to make in order to do that, right? And then, of course, you have some design choices you have to do, right? So when you're running an application, do you want the user to have input, or do you want the AI model to not to be able to change the results of the AI model? Do you show a heat map? Do you show much more specific coordinates? And then, of course, you know, you have to have all your code repositories, your integrations, and you also have to do, so before you do that, you also have to do choices about platform. Use TensorFlow for your models. Do you use PyTorch? Do you use some sort of model serving server? Do you adhere to those platforms? Do you say that we want to only support one platform? So then every model that has to come in has to be that specific format. You try to do everything, Docker. So there's a lot of choices that have to be made, a lot of things that have to be in place in order to do that. And of course, this only talks about the technical part of it and how to implement this, in a technical sense. Of course, you have to, when you bring new changes, you have to do the change management. So if you have a friendly department, then it becomes easy because everybody's already acquainted with the new technology, they're all acquainted with change, and they are actively want to participate. You can find this in an academic environment. Not every environment is an academic environment. We're not always talking about AI for the few. We always want to look, okay, how can we do AI as broad as possible? So then you have to look into, how do you manage this change? And of course, you have to have, to reserve time to do a specific project. So when you have a specific or a new model, make sure that, first of all, who's going to be benefit by this, who's going to be affected by this. You have to identify the stakeholders. And of course, once you put things in practice, you have to be able to support the people and the process, of course, be able to show, okay, this is how it works, first of all, training. But then second of all, this is what it does to your workflow. And of course, you always have to, adjust the expectations and also the size of the project. You can't start with saying, we're going to replace a complete workflow, existing workflow. You have to start with, supplementing and, doing incremental changes. So in our department, we first want to start a bit small, let's say. So we wanted to, choose an application where we have a good affinity with, and we wanted to, use the tools that we already have to try to kind of avoid, in the first stage at least, really, really difficult questions or the difficult issues. So then we first tried to do this through our packs, meaning that we use the built-in API of our packs in order to do the AI model implementation. So at the moment, we were doing a pilot implementation for a mitosis detector, which is available for the user through the viewer. That means that the user has to start it. So no background workflow implementation. And how this implementation looks in a sort of technical way is that you first, at one side, you have the AI model, the computing environment, and the infrastructure, servers, and storage, and everything. And then you have the packs on the other side with the user. So then when the user does an action, it sends a message to the packs, and then the packs communicates with the AI model in order to share the image data and then return the results to display them to the user. Now, what's good thing about the current system we're using, the Sectra packs, is that you can quite easily add applications yourself. So you can, every application that you have or every AI model, you can add as an extra application, and this shows up as an extra option. And then this way, you can very easily make sort of small micro services, which then so it's much better for your architecture to work this way. So we first started with the mitosis detection algorithm, which works on H&E images, and the model was developed by the Technical University in Eindhoven. This was based on training data from our department and from public challenges that we've participated in the past. And the way to use this application is you right-click in the main viewer, then you select the interactive mitosis detector, and then it pops up with an annotation tool where you just select the area where to do the analysis, and when the analysis is done, you get the results. So this is a example of results. On the left side, you see the results of the classification. Then you have two classes, which is mitosis and negative. So the model also gives you an indication of what it thinks that it's negative, but it's still it's a high chance of being something, right? So we have a lower threshold and a high threshold. So this is also to good for pathologists, so they can see what is missed by the model. So they see what the model shows as negative, and then they can themselves, in a clear overview, decide if something should be in the right class or not. And they can also drag the results from one class to the other one. So if they agree with the results, it's fine. But if they don't agree, they can select the patch from above and then drag it down or the other way around. When they're done, they click mark as verified. So there's a small button up there, and as soon as they do that, then you will immediately see the overview, and then it shows you how many mitoses is for a specific area. So at the moment, we have this running on a simple workstation with 2 GPUs, and it's not very fast because it has to do the analysis on the highest magnification, so 40x, and that takes a lot more time than if you would do the analysis on lower resolution. So it has to analyze a lot of pixels. So on 2 GPUs, you can do a 2 square millimeter area in around less than 60 seconds. So the more GPUs you have, or the bigger the cluster, the faster this is. So it's scalable with the amount of GPUs you throw at it. And the good thing about this is that the model, or the system that hosts the model, is separate from the PACS, so it doesn't really affect the performance of the PACS. They only communicate through standard protocols. So then, if your PACS cluster is fast enough, you can communicate very high speed. You can get all the data in a short show. So then the latency between requesting results and getting them back can become quite low. So before we implemented this model, we first ran it onto some validation and testing data sets, and it performed quite well. It had a very high performance. So then we chose out specific variation of the model. And now we're running a pilot study in our production environment with a single observer in order to see how well it works in actual practice with new data, so data that it hasn't seen before. So we're doing first so we first starting with the traditional workflow, which is counting on glass, right, and comparing that to counting digitally, so on the screen. And then comparing those methods with the AI assistant. So when you do counting using the AI model. And so far, we've seen that the agreement between these three methods is, it's almost perfect. It's above 0.8. So the kappa between those is very, very high, which means that the assistance with the AI model is actually very good, right? So there's no huge discrepancies. But so what we want to do, basically, the next step is, okay, this is with one observer, and this observer agrees very well with itself across all three methods, and we're currently trying to figure out what is the agreement and what is the difference between these methods. So the next step is to do multiple observers and do a more bigger validation and see actually how well does it perform. The good thing about this algorithm is that it's not very authoritative, meaning that you request analysis, but it doesn't really say, okay, this is it, and you can't really. So you have actually an interaction with it, and you can change it. So one of the most important questions is, first of all, what is the chance that when you're using this model, you will miss mitosis, right? Because that's the most, that's the hardest thing that can happen. And the question is that it's not really a problem, meaning that you get a good overview from the results, but then you can also zoom in and check for yourself, and it's very easy to annotate things. And then the second question is now, is this model faster or not, right? When you use it, or does it require so much involvement that it takes much more time? And the answer is it's actually much faster. So that when the pathologist uses this model, he can do the mitosis counting much faster than he would do it traditionally, either with a glass or just counting manually. So that's already a very positive thing. So basically, what I want to say is that the application, the AI model application, is actually quite complicated. It involves a lot of moving parts, and it needs people with different skills in order to implement it. And like with a lot of things, a lot of projects, and that are presented, it has this iceberg quality of it. That very few things, you see very few things, and below it, like below the surface, there's like a huge mountain of things that need to be considered. But seeing the first results and seeing how promising they are, I would expect that this is not a situation which will slow down, and I think the uptake is going to become quite faster in the future.